transplant, which is crucial to the treatment of diabetes. And as I say, the CV just goes on and on. So thank you so much for giving us your time this evening, Dr. Soon-Shiong. And may I hand over to you to talk to us on cutting-edge technology and 21st century medicine during the COVID-19 pandemic. Thank you once again and welcome.
Thank you for having me, and what an honor to give you the memorial lecture. Maybe I should start with, if I could have the next slide, with really the history. As you could see, I've had the privilege, as I said, to be trained by some of the giants of medicine in the slide, and graduated in 1975 at Wits, and then completed my internship both in medicine and surgery, and specifically in medicine under Professor Botlhale. Next slide, please. And I think, I've shown the slide before, but after 1977, I decided to leave the country so that I could learn more about both the immune system and technology. And on the right-hand side is a brief history of the quest, going first to University of British Columbia, where in 1992, the natural killer cell, NK92 cell line, was discovered. And then moved to UCLA in 1980, and was fortunate enough to receive grants from NIST and NASA, and became a NASA scientist as part of my medical curriculum at UCLA. And we'll talk a little bit about some of those inventions. And then developed this nanoparticle, which really forced me, so to speak, on the right-hand side, to go into the world of manufacturing of injectable products, because a nanoparticle had never been developed. I think that stood me in good stead. I took over this company called American Pharmaceutical Partners, which we founded, and was able to grow it to develop about 150 FDA-approved products, and we manufacture 1 million vials a day. And I think in today's world of pandemic and need for global scale manufacturing capacity, that really gave me a fantastic grounding. But really the reason I built that infrastructure was to build this nanoparticle, Abraxane, which now, sadly, I just heard last week, there's a global shortage of Abraxane. So with that history from 2010 to 2021, so it's a decade, more than a decade, actually. The quest was the bottom, to identify how we could activate the immune system of the natural killer cell, the dendritic cell, and the memory T cell. And these three cells you see at the bottom of the slide has been the pursuit, because I really believe that this is the opportunity, using or understanding the fundamental science of these molecules and how they interact, could change how we treat cancer and infectious diseases. So the next slide, please. I look at some of these slides and go back in time, and here we are in 1993, where what you see in the middle is this human islet cell that makes insulin. And we pioneered the development of this encapsulation system using a seaweed called alginate. And our two patients, we were able to get totally off insulin. And this then really became the pursuit of understanding the immune system, because in the world of the pancreas transplant, as you see through this microencapsulation, my goal was to subvert the immune system. The goal was to overcome or suppress the immune system. And in fact, that's what viruses do today. The conflict I had was, next slide, I was also a pancreas cancer surgeon. And in that case, my goal was to activate the immune system. And here in 1990, we published this paper at UCLA, where we identified the cell then called the cytotoxic T lymphocyte, a natural killer cell. Really was, we didn't identify the cell was there, but it had never been really fully understood at how it worked. And one of the things we discovered using the encapsulation technique is the natural killer cell kills either infected cells or tumor cells by direct contact. And thus began the journey that we really need to understand this immune system. Next slide. And in order to do that, we needed to get what I call into the tumor microenvironment. And I think there was a lot of, I suppose, assumptions that if you inject something into the vein, somehow it gets into the tumor. Well, it turns out it needs to cross a barrier called the blood vessel wall. And so we studied that blood vessel wall, and it turns out there's a receptor called GP60 on the blood vessel wall. And this was part of the NASA scientific experiment, because as I was developing stem cells on the NASA space shuttle, my co-scientist was developing the structure, or understanding the structure of albumin. And the light bulb went on that the opportunity to take albumin and create a nanoparticle encapsulating this poison called paclitaxel and be able to penetrate the blood vessel wall. And now you bring the cancer and the therapeutic agent in close proximity. So the whole concept at that stage in time was starve the tumor, and here we're saying no, feed the tumor. And I think that's the lesson, that going against dogma is not necessarily negative if you really are following the science and persist. And that's what we did with regard to Abraxane. Next slide. And I'm pleased to say that the molecule got approved in 2005 and got approved for breast cancer, lung cancer, and ultimately pancreatic cancer. And it now sits in the Smithsonian, and the National Museum of American History looked at American journeys of immigrants. And I'm happy to say that this file now sits in the Smithsonian. Next slide. Which then says, by 2010, I had the freedom and truly the luxury to say, now I really want to figure out how could we harness the immune system. So my next few minutes or half an hour, we'll spend the time talking about harnessing this immune system. And it looks pretty simple. There's these natural killer cells in your body. There's this thing called the dendritic cell in your body, and there's a memory killer T cell. There's actually a memory B cell. There's actually a memory natural killer cell. And if you start understanding and going way back in history, you began to see that the natural killer cell and the dendritic cell is called the innate system, and the memory T cell is called the adaptive system. And what was remarkable is that the innate system has an evolutionary life of 1.5 billion years. And only one modern man arrived on Earth 400 plus million years ago was the adaptive system, which is the T cell, did that evolve? And this speaks so much power to the fact that this natural killer cell, that it's been around in invertebrates. And as you'll see from a slide I'll show, that insects and invertebrates represent over 80% of the species on the planet today, and have been around for 1 billion years, and are completely resistant, very resistant to every infection, whether it be bacterial, whether it be protozoal, whether it be viral. So trying to understand how this evolution has occurred in us, and more importantly, trying to understand how to interrogate how they talk to each other. You see all these dots called chemokines, cytokines, and what I call the dance of proteins inside a human cell. I started drawing these things up, first in my mind, and then reading and understanding and looking back on and all the findings. And I asked Professor Shabir Mahdi yesterday, how deep do you want me to go into the work? And said, fairly deep, but keep it not too deep. And I said, okay. the next slide is for me to really speak a little bit about the natural killer cell. And I'll try to keep it at a high level, but in order for us to really explain how we've developed this technology over the last decade, I'll try to go to some level of depth. But on the left-hand side, you see what I'm talking about, that this natural killer cell has been here since the Cambrian age, 1.5 billion years ago. And in invertebrates, it was in sea anemones, in worms, crustaceans. And this is Professor Hoffman's slide, which I've adapted. And as you see, the natural killer cell and dendritic cell on the right-hand side was the innate system. Only when vertebrates arrived was there then an adaptation of the adaptive immune system, where the dendritic cell would then activate a T cell and enable memory killer T cells. So this is the trifecta that I've been trying to understand. And let's speak, next slide, a little bit about this complex system. And as you could see, the system is much more complex than those three slides, those three pictures. The innate system is the natural killer cell, the macrophage, the dendritic cell, the mast cell, granulocytes, and in between is even the thing called a natural killer T cell, and on the right-hand side, a B cell and a T cell. Now, for today's talk, I know it was about COVID. If you look at the B cell and antibodies, this is where the vaccines of today have been focused. But we really need to have a broader immune system that not is just the antibodies, but the T cells, and specifically the CD4 and CD8 T cells, so that we can get memory. And we'll speak a little bit more to that. These cells are incredibly complex in how they talk to each other, what I call the dance of proteins. Next slide. And trying to address this simplistic system. Next slide. And I don't expect you to read this, but this is what, when I was drawing on many boards, and I said to Dr. Mahdi, okay, I'll give you a board that how I thought about this. And this is what I call the dance of proteins and how those all interact, whether it be a tumor cell on the left-hand side. And if I may draw here, I will draw this tumor cell and how this tumor cell interacts with the blood vessel. And since 1990-95, how we worked on getting through the tumor microenvironment so that we can activate these cells and really activate the natural killer cell. And here in 1992, we discovered the cell line, but really now can grow the cell to get a memory in that natural killer cell, which is now, in fact, I'll show you for the first time in 2021. But we want to then engineer the natural killer cell. We want to create a killer T cell and suppress the myeloid-derived suppressor cells and Treg cells and activate the dendritic cell and activate the B cell. And this crazy map of what I call dance of proteins is we termed quantum oncotherapeutics. And the reason I created this name is because everything we do to anything as we treat a patient, all these interactions really change in real time. So each of these cells have a life to themselves where they can transform quite dramatically. And this complexity lives in a single cell, yet we need to understand the whole host. And we need to transform this to 7 billion people and create what I call predictive modeling and create what we call an infrastructure so we can create that. And thus was the quest that I had the luxury of a decade to try and work through and really try and drive this for both cancer and infectious diseases. So let's go to the next slide. And I think that's as deep as we will go. Obviously, this slide alone could take me 3 hours just to walk you through the thought process. But by 2016, we decided to go ahead and file this concept because it's so non-conventional of how we would change cancer care. And I'm happy to say in July of this year, this patent got issued now. So it's there for all to see, the details within which our thought process has evolved. Next slide. So let's talk a little bit about the natural killer cell. Next slide. And the history of the cell. The first thing is about this thing called the NK cell line. And this goes way back. And, you know, this is so much about science. We stand on the shoulders of giants, and no single idea is a novel idea. It's really an evolution of thought. And here in 1909, Paul Ehrlich had the hypothesis, and correctly so, by the way, that tumors occur at a high frequency in humans. And in fact, it does. If you take your your stem cell, in order for the stem cell to occur, the amount of mutations mathematically that would happen as errors, the cell would recognize that. And they're kept under control by the immune system, he says. And it turns out it kept under control by the innate immune system, by the natural killer cell that would see an MHC1 defective cell, etc., and kill it. So as you're walking around, as we're all walking around today, we're generating, so to speak, transformed cells. And yet we're not walking around with tumors, hopefully, because you have active natural killer cells. So this is not a new thought, that the body has an innate protective mechanism both against cancer and infection. Next slide. And then Dr. Hans Klingemann, while at University of British Columbia at the BC Cancer Agency, discovered a patient with a cancer of the natural killer cell and had the foresight to grow that cell. And that became this NK92 cell line. Now you have a cell line that you can grow in an unlimited supply and genetically engineer. Next slide. And we did so. And this was then, we placed into the company, which is now known as Immunity Bioscience, so IBRX, in which we took a natural killer cell, cell line, and we modified it, in this case with HER2 antibody, so that it could recognize this breast cancer cell, but not recognize a normal cell. So if we run that video, you'll see the cell literally avoiding the normal cells, finding the target, and through its enzymes called granzymes and proteolytic killing factors, it literally, quite literally, dissolves, and it's quite literally a serial killer. The next slide will show you a little bit more detail, and quite exotically, the red is the natural killer cells. The green is a breast cancer cell, the MDA-MB cell line. And when the cells die, they would turn blue based on the dye that was developed. And within these natural killer cells, it would track the granzymes. So here you see the granzymes and the natural killer cells tracking these and quite literally killing them. And so this now, with the aid now of modernized microscopy, and on the right-hand side, you sort of see the direct cellular interaction. You see the granzymes quite literally being inserted into these cancer cells and killing it. And what's remarkable, we're born with this. We have this capacity. So if we could harness this natural killer cell by activating a protein called IL-15, or if we grow this natural killer cell off the shelf and have an unlimited supply, we could transform cancer care regardless of the tumor type. Next slide, please. And this is what we did. We actually developed huge large-scale manufacturing capacity so that we can grow trillions of these cells and isolate them into a bag, which this technician is handling, which holds 2 billion cells, and then just thaw them at the bedside and hang them. The idea being that this now could be shipped around the world. This is now a universal cancer killer without high-dose chemotherapy, and the ability then to truly, I think, change the paradigm in cancer care. Next slide. And in 2017, we performed our very first infusion. Next slide. And had already built then, by now, the capability of not only growing trillions of these cells, but creating these cryofarms. I think this is a video to show you the scale now, the ability to now store trillions of these natural killer cells, all barcoded GMP, and have the ability then for these trillions of natural killer cells to be transported anywhere in the world, so that this could be given to patients and really leapfrog the transformation of cancer care. Next slide. And as I said, by August 2017, our very first patient was infused with metastatic pancreatic cancer with natural killer cells. And by this process of taking the cell line, thawing it, ready for use off the shelf, and literally hanging it as an outpatient for 30 minutes. Next slide. And what we've done so far is infused over 1,300 doses across multiple tumor types: breast cancer, lung cancer, pancreatic cancer, head and neck cancer, bladder. And to our real excitement, I'll show you our proof of concept. What I'm showing you here, though, is a very complex biological manufacturing process. And this is what I mean by know-how, about the ability to transform this kind of manufacturing process to South Africa. And that's our goal, to bring this home, so to speak. That's a promise I made when I left the country in 1977, that we would now go and bring this kind of technology and more to the nation, and let South Africa be the technical hub of all of Africa and perhaps even the world. Next slide. As I said, to date, over 100 patients has been dosed. Over 1,300 doses have been given, 2.7 trillion cells infused, and not a single patient had a cytokine storm. And next slide. The next chapter was, could we even take a patient and do what we call apheresis, just like a blood donation, and remove the white cells, and then purify those white cells into natural killer cells, and then activate those natural killer cells and generate what we call almost a stem-like natural killer cell, called a memory natural killer cell. If we could do that, then this is an autologous or an allogeneic method of doing that, with just growing them, storing them, very much like cord blood, which means then that the best thing to do for every human being on the planet is to have your natural killer cells stored, because as you age, or if you get an infection or you get chemotherapy, you actually wipe out the ability to actually produce these natural killer cells. So we embarked upon that, and I call that MSANC, which is memory cytokine enhanced natural killer cells. And I'll show you next slide. The process. Now we've developed this process, and I'm pleased to say FDA has given us approval, and we've now initiated our first in-human clinical trials. On the left-hand side, you see a patient in our clinic with quite literally an autophoresis, meaning apheresis, on this machine, and a bag of blood is extracted of just pure white cells. And we can then aliquot that into 10 lots, and then go through our process, and by day 17, we can be able to take one lot, one bag, and freeze the rest and storage, and end up with 1 billion cells, which then can be frozen and hung at the bedside. This is now what we are doing, and the opportunity then to have autologous and allogeneic natural killer cells, which at some point we could even engineer to make them targeted, But what's different about these cells? Well, what's different about these cells is these cells are potent killers. We've partnered then with the National Cancer Institute in the United States, and they found that these cells were able to kill every cell line that they were able to put against. So we then developed a technique of creating what we call tumor spheroids, taking tumors and growing them into spheroids and spheres, and then putting these memory natural killer cells against these spheroids, which is much more consistent of an in vivo when you have a tumor mass rather than a single cell. Next slide. And if you look at the next slide, here is the growth of our spheroids, and if you can play that video of how we grow these spheroids, these are the tumor cells. And as you could see, it now becomes a mass, like a tumor mass, a bunch of cells. And the challenge then is how do you kill that spheroid? Well, we then insert our natural killer cells, of these memory cells that we've grown from a patient's own blood, peripheral blood, and that video will play. And this is really an unpublished video, and it's remarkable how these natural killer cells are such potent killers of this mass, and as you see this mass reducing over time lapse under the microscope. And I'm really very, very excited about this this technology now, and then this will then bring us, I think, to this next level of natural killer cells. So then this brings us to the question is, well, this is all very nice. How real is this? And again, the luxury of having the freedom to go and prove this concept and the foresight of the FDA, and I give credit to Dr. Pazda, who saw that vision together with Janet Woodcock with regard to what we call a common master protocol. And what I mean by that is if one could have a common master protocol of treatment of activating the natural killer cell, and activating the dendritic cell, activating the T cell, CD4 T cell, and the memory cells, and the B cells, and the antibodies, that requires multiple novel agents to be coordinated and orchestrated. And that was the QUILT trials, QUILT trials, which stands for Quantitative Integrative Lifelong Trial. And we began that adventure. And I'm pleased to say the results I'll just share with you, which is really a proof of concept that, in fact, this common treatment protocol of that concept could cross multiple tumor types. And as you know, bladder cancer in Africa is one of the most devastating diseases. Over 180,000 people are diagnosed a year, hundreds of thousands of people die a year with schistosomiasis in Africa and Egypt. In the continent of Africa, it's one of the devastating diseases. We then chose diseases that we knew were very difficult to treat. Merkel cell carcinoma, which is a very aggressive form of a melanoma, metastatic pancreatic cancer, triple negative breast cancer, head and neck cancer that failed everything. And we took these 1, 2, 3, 4, 5, and even more, and I'm just for the purposes of sharing this with you, cancer profiles, but in large numbers of patients who had failed everything. So they failed all their standards of care, first line, second line, third line, fourth line, fifth line even, and subjected them into these QUILT trials. And I'm going to give you very brief data now. Next slide. And let's talk a little bit about bladder cancer. Next slide. And the concept here is the standard of care is BCG. But it turns out our belief is that what BCG does, it actually induces what we call PAMPs and DAMPs, very much like any infection. And when you have PAMPs and DAMPs, and guess what happens? You end up with a natural killer cell, which is exactly what the invertebrates and insects have been doing for 1.5 billion years. We had then developed this molecule called IL-15, whose activity is to activate natural killer cells and T cells. So we took patients that had failed BCG therapy and then gave them BCG again and induced the activation and now enhance the activation with IL-15 so that these natural killer cells would activate and induce what we call immunogenic cell death. Well, what happened? Next slide. In our phase 1 trial, there were complete remissions across every dose that we tried. This to us was very exciting. 9 out of 9 patients, bladder cancer. These happen to be the naive patients. Next slide. And based on this, the FDA granted us fast track designation, and we initiated our regulatory trial. And this is a data that's now public. A data cutoff is of May 19th, and obviously we have now, it's now September. But in the patients that were accrued, 0% treatment-related SAEs, 0% immune-related SAEs, and 0% grade 4 and 5. So clearly a well-tolerated safety profile. But what's more exciting, next slide, was the finding that of the 81 patients that were enrolled, 72% had a complete remission. So we had met the primary endpoint. Recall, these are patients who had failed BCG, and the only opportunity left for them, sadly, is a cystectomy, meaning removal of the bladder. And so we have an over 80% avoidance of cystectomy and a durable remission. Next slide. And when we compared this to the approved drugs, Pembro and Valrubicin, it really looked very favorable with a 72% complete remission rate at any time versus 41% and 18%. But more importantly, a 0% immune-related adverse events. Next slide. So there was a clear proof then that just by activating the natural killer cell and T cell with a single infusion of this IL-15 molecule we have. But what if you then took either the IL-15 molecule or the IL-15 molecule plus an NK cell and Merkel cell carcinoma, and I apologize in advance for the next slide, which is a very painful slide, but you'll see the aggressiveness. And this patient came to see us. Patient was treated in Seattle with, and you see recurrence number 1, and then recurrence number 2, recurrence number 3, recurrence number 4, after multiple treatments, recurrence number 5, and then came to see us after recurrence number 6. The next slide. And I was happy to say that within 14 days, we began to see a response to our natural killer cell and a complete response within 3 months. And now, no treatment since July 2019, and now the patient's over 5 years with complete remission, which then speaks to memory, because clearly, other than receiving this treatment and a checkpoint, which we've added, we've induced memory in this patient. And we are now developing these as a registration trial for Merkel cell carcinoma. Next slide. Let's turn to pancreatic cancer. And as all of you know, the survival rate of pancreatic cancer is devastating. And Abraxane got approved for pancreatic cancer, but that to me was not sufficient. Next slide. So again, if one now could take this concept of activating natural killer cells with a off-the-shelf NK, here's a patient that failed a standard of care, and this thing called a CA19-9 level, within 3 months went to normal. And by PET scan had a complete response and continued by month 4 and continued by month 8 and still on continued by month 11. And next slide. Again, incredibly encouraging that within 125 days, we can convert a patient that failed all standard of care in pancreatic cancer, metastatic pancreatic cancer, to complete remission. Next slide. And then finally, 2 more, triple negative breast cancer, a very difficult disease to treat. And as you could see, third line, we had complete remissions in these patients, again, with the same therapeutic protocol that basically we use for pancreatic cancer. Next slide. And then the same protocol we use for patient with head and neck cancer. And this is a patient that was the family was told that the patient should go to hospice by two of the major institutions in Los Angeles. Next slide, and came to see us. Next slide. And the patient unfortunately had a very terrible tumor under the chin and as well as the side of the neck, of the head and neck, ulcerating through. And after our treatment, had a complete remission. And as you can see by CAT scan, a complete remission, merely after 2 cycles of the treatment. And this lasted for over a year, and the patient was able to eat thereafter. Next slide. So I think the idea that harnessing this immune system and bringing together this crosstalk, and to cut to a simplistic chase here, that we ended up with 4 products, and basically cellular therapy. And the idea then, if you combine that with RNA, and especially self-replicating RNA, and DNA, whether you administer it through an adenovirus and adjuvants, we would then have the tools across the board to really manage both, on the left-hand side, if your video plays here, the cancer-infected cell, and on the right-hand side, even a virally infected cell. And I see that it's the same, treating a virus with a killer T cell. Again, the other video on the right-hand side. You'll be able to have a therapy that can cross infectious disease, whether it be schistosomiasis, whether it be TB, whether it be cancer, as a common treatment protocol, because we were born with this innate mechanism. Which then turns me to COVID. Next slide. And time doesn't permit for me to go deep into COVID, but when we saw this, we really took a left turn, because we were really developing vaccines for Zika, HIV, and really at the time when COVID hit, we saw that both the spike and the nucleocapsid. But it was really clear to us that we needed to actually address both, because if you could address both, you could have long-lasting, durable immunity that would take you into what we call a universal COVID vaccine, because these spikes would mutate. But the nucleocapsid itself has less chance to mutate, and without, if one could then create a vaccine that had that kind of combination. So I saw COVID as not a sprint, unfortunately, but a marathon. Next slide. And that we needed to understand how not only this virus works, but DNA, RNA, and protein. And this is what we call the general dogma in your human body, that you have DNA that translates to RNA and to protein. And the DNA translates inside the nucleus, this translates inside the cytoplasm, and this goes on the surface and secreted and in the blood as a protein. So if you understood that that is the biology of not only how the virus works, but how one could generate potentially a vaccine across a modernized vaccine, and create a vaccine that could activate either at the DNA level, or vaccine that could activate at the RNA level, or vaccine that is basically a protein subunit, but you then add adjuvants. One of these three, or the combination of these, could generate what we call a universal COVID vaccine, and overcomes the mutations, and really take a long view to prepare ourselves not just for this pandemic, but the next pandemic, and going from lambda to delta, now to mu, and beyond. So next slide. We've taken that approach, and sorry, I'm trying to erase this board here. And we've taken that approach, and now we have a different quest. And the quest is for a universal durable COVID vaccine. When I say universal, I mean a vaccine that will cross-react with the wild type S to the lambda to the delta to the Brazilian to the mu, and even to the next COVID. And durable in the sense that you would have T cells and memory B cells that would recognize an attack. So we have the Sasonki Boost trial, which I'm pleased to say is in phase 2 now, with where we're boosting healthcare workers in South Africa. We have submitted now the TEMBA trial, where the DNA and the RNA vaccine are being combined. And soon we'll be submitting the protein TEMBA 2 trial, where the subunit protein and the adjuvants will be submitted, so that there'll be 3 platforms, DNA, RNA, and protein. The ambitious goal is not only to understand all of these and the combination of what we call a heterologous vaccine, next slide, but to manufacture them all in South Africa. So here is the RNA vaccine, which is basically a self-amplifying RNA with a very novel nanolipid carrier, which has an adjuvant, is adjuvated within its core, combined with a DNA vaccine, which is second generation adenovirus. And on the right-hand side, you see, I'll refer you to the details of the paper that just got published in Frontiers in Immunology, which has now we showed with Botlhale and Botlhale and NIH, that we're able to completely remove the opportunity for virus to infect the nasal lung passages after a challenge. Next slide. Let's pass on this slide. This is the details that I'm not going to get into. And then finally, the RBD protein, subunit protein, which we've now manufactured in yeast in large GMP methods, together with the adjuvant, is now ready. And as you see from this publication in Science, that it's now protective in non-human primates. Next slide. As you said, the technology to manufacture this is complex. We've built this and we're ready to bring this, transfer this both upstream and downstream to South Africa. Next slide. So finally, this is my final slide, that as you could see, this journey has really enabled us to learn a lot and bring in technology. And the goal now is to take all this learnings and leapfrog and bring it back so that we can transform how we treat both cancer, next slide, and infectious disease. And again, I want to thank my gratitude not only to WITS, but the people that trained me. Professor Duplessis, who gave the ethics lecture every Friday and really pioneered the opportunity for me to be the first Chinese ever to work in the Johannesburg General Hospital. Professor Bothwell, who stood at my bedside as my first patient, refused to let me touch him and allowed me then to be trained as his intern. Professor Tobias, who has inspired all of us about being the discoverer of the modern human. Professor Barlow with the Barlow syndrome, Professor Seftel, his wonderful talks on infectious disease, and Professor Myberg, who inspired transplantation. I want to thank these professors and thank you for giving me the opportunity to give this talk.
Thank you, Dr. Soon-Shiong. Brilliant talk. It sort of takes us into science fiction in a field of oncology, so thanks for that. So we've got a few sort of questions, and if you don't mind, just give me a second.
Sure.
So the first one, I think you might know this alumni, Arnold Sinman, thanking you for the amazing work that you've been doing. The question is, how do you see this as a therapy or as a vaccine for prostate cancer? Or are you working on any other sort of therapy for prostate cancer?
Yeah, actually, we are in trials with prostate cancer together with Dr. Jeffrey Schlom and Dr. James Gully at the National Cancer Institute. We've taken our adenovirus with PSA and shown that patients who had failed in enzalutamide failures have a significant drop with the PSA. So absolutely. I think the concept that this is tumor and anatomically tumor related, I'm trying to break that dogma. While clearly there are different tumors that may have different immunosuppressive environments around them, the activation of the immune system to kill, whether it be a prostate cancer, breast cancer, lung cancer, we find, as I said, this common therapeutic opportunity. So the opportunities are enormous. So the answer to that is yes, we're in trials in prostate cancer and we're seeing very promising results.
Okay. So, Patrick, my apologies. I probably should have introduced myself to the audience. So I was so excited about your talk that I forgot to introduce myself. For those that have joined us, my name is Shabir Mahdi. I'm the Dean at Faculty of Health Sciences. I started in a position in the beginning of this year, but I didn't really want to detract from the importance of engaging with Patrick. So please do excuse me. Patrick, perhaps something separate from cancer. We'll come back to many of the other questions around cancer. What do you see as being the barriers to islet cell transplants in diabetes besides costs?
Well, I think, when I did at UCLA, I did the whole organ pancreas transplant, and people are still doing that. It really scared me because, fortunately or unfortunately, diabetes is a chronic disease that you can survive in if you manage your hemoglobin A1C. I think the inability to get enough islet cells, and an islet cell is not a cell, it's an organoid. It has a pancreatic polypeptide cell, glucagon cell, and it's an interaction. It's not as simple as just an insulin-producing cell itself. I began to realize that, and we did the first stem cell. So if the deficiency is merely just insulin, there's now capacities to create truly mechanical devices of insulin pumps, but more importantly, now with the ability to have a service system of even. So I think that's where it's going to really, until you can really get these pluripotent stem cells to really take and inside the liver, etc., and also avoid the immune system. So I think that's what's really held back islet cell transplants. The inability to get enough cells, the complexity of that pancreas, which is an amazingly complex organ, and then the rejection of those cells by your body, by your immune system.
One of the intriguing things to me is that when you're dealing with such bulky tumors where you've got this metastasis, how do you explain the absence of having any sort of a cytokine storm, the equivalent of an autolysis type of syndrome on chemotherapy?
Yeah, so if you look at the T cells of the current T cell, the CAR T cells, and the induction of cytokine storm, because of the absence of balance, the natural killer cell really together with the T cell really appears to create this balance, because the natural killer cell has both inhibitory as well as stimulatory receptors. So your body, if it's unbalanced, you'll end up with autoimmune disease. So I think what we have in the context of a natural killer cell is providing the balance so that you don't get the cytokine storm and yet you get the killing and the direct killing. You know, the Asian mentality of the yin and the yang is real. It's very real. 2,000 years of balance. And so I think all I can say is we do not see a cytokine storm, and we see the positive effects of the killing.
So do you see natural killer cell therapy as being an alternative or replacement to chemotherapy, or do you see it as being a supplement?
So I use chemotherapy in a very different way. So people have been trained for 40, 50 years to use chemotherapy as a cytotoxic poison to kill the cancer cell. I think you win the battle very shortly, but lose the war, because as you kill that one cancer cell, you release the clones of the resistant cells and you get metastasis. Now, counterintuitively, what that means is that we may be inducing metastasis with high-dose chemotherapy. Now, that's a very scary thought. On the other hand, if you take chemotherapy and you use the lowest of lowest dose not to kill the cancer cell, But to kill the cells, it's suppressing the immune system, such as the Treg cell, the myeloid-derived suppressor cells. And you use the chemotherapy to just stress the cancer cell to induce what we call damps and pamps, as if that cell is infected, and express the receptors and the targets. Because what the cancer does, it hides. So I talk about hide me, find me, kill me. And I go then to expose me, find me, kill me. And the expose is using a very low dose of chemotherapy as a chemoimmunomodulatory effects. So we use what we have, but smartly use what we have by understanding the biology of what it's doing. So unfortunately today, an oncologist is not a virologist and not an immunologist. And a virologist is not an oncologist, yet it's the same science. So there needs to be a crossover in thought between an oncologist, a virologist, and an immunologist. And that's why I said COVID is cancer and cancer is COVID.
Okay. So how do you envisage shutting down and then rebooting the immune system in the management of autoimmune diseases? Would this be a once-off process, or would patients be required lifelong treatment?
Well, we're learning this. The beauty of this, for example, we have a metastatic pancreatic cancer patient now 10 years, 20 years, 12 years, I beg your pardon, alive. We have the patient I just showed you still alive, almost 2 years. I'm not sure when to shut down the activation of the natural killer cell. And so we're able to inject the patient literally with what we call a booster shot of IL-15. It's a subcutaneous injection. Come in as an outpatient, you get a shot. The patient with the Merkel cell stopped treatment in July 2019 and still is in remission now in 2021. That's the next chapter for us, is how long do we have memory cells? How long do we have memory NK cells? How long do we have memory T cells? How long do we have memory B cells? And what's exciting now is our group, together with our collaborators, are developing tests, just like a diabetes test with finger prick or from your saliva. We can measure your memory cells, and that's where we're going next. And this is going to be important for vaccinology as well, to know how long is your vaccine lasting. So unfortunately, it's an unanswered question yet, but we're getting there soon.
Thank you. Patrick, something obviously very close to the heart of many people in the African continent is an issue of access. And the question is, with the NK cell technology, it seems evolutionary, but will it be within the reach of public health services in developing countries? How do you see the whole issue of patents, royalties being addressed in a context of low middle income countries with this sort of technology?
Yeah. Well, look, I think these inequities is really, I don't know how to say it, an absence of enlightenment of humankind yet. We're not 1.5 billion years in evolution. We're only 450 million years in evolution. So this idea of creating these inequities across developing countries, when all boats rise, if we help all. So the opportunity for us to bring, at least I can only control what we can control. And that's why I took the unusual step of going for a decade and trying to bring as many of these technologies under our roof of called networks as possible, so that we would have the freedom to operate and bring it into South Africa and provide it all the way up and down Africa. That's what we intend to do. And that'll hopefully overcome these barriers.
Patrick, have you had any experience with the therapy in multiple myeloma?
Yes, we do, actually. And this actress from India has put herself up. I won't name her name, but she's put it out very publicly, and she's gone on Twitter, she's gone on YouTube. She received our natural killer cell after having failed multiple myeloma treatment and is in long-term remission. And I can't tell her name because she allows us to do that. Her name is Lisa Ray. And she's put her cells up on YouTube so people can go watch that. She's a wonderful spokesman for multiple myeloma.
What's the possibility of graft versus host reactions related to NK cell therapy?
Well, unlike T cells, right, where the NK cell doesn't require T cell receptors, and there's no graft versus host disease activity in that sense. On our NK cell line, the NK cell lives only for 7 days because we radiate it, obviously. In the autologous NK cell, it's your cell. And the allogeneic, it's your cell. It's the T cell that gives you graft versus host disease because of these very complex things called MHC1, MHC2 restricted epitopes, but we won't go there. But the answer is the NK cells don't induce graft versus host disease.
Okay, so Patrick, I know that we've got limited time with you. How much more minutes have you got to spare for us?
Sure.
Can we go on for a few 5 more minutes?
No, sure. I'm happy to do this.
Great, thanks, Patrick. So the next question is that BCG has usually been administered with the intravesical route. The question is, why have we not fully explored the newer modalities via the same intravesical route for bladder cancer?
Sorry, Shibe, I didn't quite understand you.
In the treatment of bladder cancer, BCG is usually administered through the intravesical route.
Right.
Are you considering using natural killer cells via the same route?
In fact, that's how we do it. So at the time the patient received the BCG infusion, our natural killer cells infused alongside it. And that's why it's a beautiful local effect and with zero systemic toxicity in the patient.
Okay. So Patrick, the golden question for all of us in South Africa is what type of investment was made around you and what sort of environment was required to allow scientists such as yourself to innovate? If South Africa was to invest in its own capacity development capability, what is required?
Well, I don't know why we've been blessed this way, but the only investment I really received was the grant from NASA and the grant from NIST when I, as part of my academic life. And then Lee Iacocca induced me to go out into the world and create the company so that we can actually build it. And I honestly believe if you really do good science and build safe quality products with high integrity, which we did with the APP, and we were able to solve the heparin crisis by providing heparin during the 2007 crisis. We were able to sell both companies, and I just used those resources to build everything we've done for the last 10 years. Unfortunately, we received zero funding, just so you know, from the government at all, not one penny, not one dime, whether it be COVID or whether it be cancer. And I don't know if that's a blessing or not a blessing, but it's allowed us really to move very fast. We have now 500,000 square feet of manufacturing capacity. And I want to come back to South Africa and do the same and bring our investments alongside ourselves so that we can move fast. And as you know, Shibe, we're moving fast in Johannesburg and moving fast in Cape Town. And the goal is to really just do it and invest the resources that we have in hand and move forward. And that's what we're doing.
Okay. Patrick, are you doing any other work on other innate like T cells, such as mate cells?
Other work like what, Shiva? Can you do that?
On other innate like T cells, other than natural killer cells?
Well, the other work is really the dendritic cell, which is really the key. The dendritic cell is the orchestrator and the macrophage is the other one. So we developed techniques where we can convert what we call an M2 macrophage to an M1 macrophage. And it turns out that's what Abraxane does. So if Abraxane is given in low dose, it converts the suppressor macrophage called an M2 macrophage into M1 macrophage. And that's with the whole thing of quantum, you know, are you alive or dead? The macrophage is the same macrophage, but can transform. And on the dendritic cell, we need to teach the dendritic cell to activate both the CD4 and CD8 T cells. And for COVID, we've taken the nucleocapsid protein as well as the S protein, and then sent them down the compartments within the dendritic cell called the phagosomes, autophagosomes, and then allow that dendritic cell to present to a CD4 T cell and a CD8 T cell. Now I'm getting very deep into the complex things that I promised you I wouldn't go too much deep on the science side, but that is truly the key. This dendritic cell is the orchestrator, and I'm really excited about that because that's where you generate memory. That's why we call it the NAN cancer vaccine, because we're going to generate memory.
Patrick, so just a few comments, and I'll quote directly: mind-blowing lecture, inspiring, and I think we'll make a photo of the amazing presentation from a true son of Africa. We'll do a snapshot of this and send it to you to glance through at your leisure. I mean, do you see this sort of therapy as being universal to all types of cancers, or are there certain types of cancers which you think this is less likely to work against?
I do. I see it being universal as a foundational piece, right? We're learning more and more because this cancer, one thing it does, it completely continues to change. And what scares the heck out of me about cancer is exosomes. It's a lifeless body that just transports the DNA and RNA to different cell types. So the answer is yes, but there's so much more to do. I think this is not a panacea that somehow we've solved the problem. I think what we've done is actually elucidated how to think about it, demonstrated proof of principle, and now we're doing randomized trials. If all these randomized trials pan out, then the answer is yes, this must be the way we now must treat cancer and infectious diseases. And the irony is, I think we want to do this from South Africa and Africa first, and then show the rest of the world. And there's a great need: cervical cancer, schistosomiasis, bladder cancer, TB, lung cancer, HIV, so Burkitt's lymphoma. So these are the kinds of cancers that we'll be able to address and make a major impact almost immediately. And I can't wait, Shabir, as we come and do this with UCT and with WITS and with KwaZulu-Natal and Stellenbosch, and really with the rural country organizations. You know, I'm going to give a shout out to Jane Simmons and what she's been doing with the grandmothers. So I think these are the kinds of things we want to bring, not just to the academic centers, but really to the community as a whole. And it can do that.
Thanks, Patrick. So just to the audience, just tons of questions here, and we are running out of time. So unfortunately, I'm needing to be a bit selective. So please don't be offended if I don't ask your question. I'm trying to group these questions into single questions. But whilst I'm sorting that out, Patrick, the other golden question, and I think you're very familiar with a joke about surgeons, is how did a surgeon end up doing what you have done?
Well, the joke is a surgeon can walk, talk, and chew gum at the same time. Well, I think I was born a South African, honestly, because as a South African, I say this honestly, is the best medical training as a generalist. You train over 7 years. You understand very deep biology, you understand very deep anatomy, and I just have a curious mind. You know, I just tweeted the other day because I was missing Kobe so much, and I started looking at his interviews. And Kobe Bryant and I had long conversations of many years, and he would spend hours just wanting to talk, and it was the curiosity of his mind. And that's what was his Mamba mentality. And so I think, you know, an insatiable curiosity in the world of biology has driven this to do what we do.
Okay, Patrick, then in terms of genomics, your view on the DNA analysis and its role in nutrigenomics?
Sorry, Shabir, I didn't understand that. In genomics?
When it comes to genomics, what's your view on DNA analysis and its role in nutrigenomics?
Well, yeah, the way we explore genomics is not just at the DNA level, because the mutated gene could just be silent. It's really what goes downstream from DNA to RNA to protein. So we really go all the way from DNA to RNA protein, and we looked at really where it's expressed on the surface or expressed into the blood. So that's the way we understand the genomics and use DNA. But really where it's exciting is when we go from DNA to RNA to protein, and then can predict which protein, which we call the neoepitope, will activate a very specific T cell. And that T cell can cure and create memory. And that is what we are working on, have been working on now, and it's already in clinical trials, called the neoepitope analysis based on DNA, RNA, and protein.
So what component of the immune system would one research to produce a therapeutic cure for diabetes?
Well, diabetes is the yin and the yang, right? So now this is where your body has created a unfortunate autoimmune reaction. Now I'm going to give you something controversial. Human beings is the only species that drinks another species' milk. When you think about it at birth, cow's milk is a different species. And I worked with a professor in New Zealand who espoused that theory and was shot down. And I think he was right, that as you drink cow's milk for a child, and goes through and you create an autoantibody to cow's milk. And now you have the NK cell trying to react, and the T cell trying to react and kill your own islet cells. So you have to go the opposite way for autoimmune disease. You actually now, instead of activating the killer side, you actually have to activate the suppressor side. So there's a whole new protein called IL-2, which is the opposite of IL-15. So I think there's a way to go there. Unfortunately, I'm going the other way at this point, but we are in phase 3 trials with diabetes, type 2 diabetes, in which we're activating the insulin-producing cell. But unfortunately, type 1 diabetes is really an autoimmune disease, and you really need to go the opposite direction with your NK cell and your T cells.
Okay. Thanks, Patrick. So I think the last question for me before I hand over to Prof. Bellet, and it's more of a comment and part question. Your confidence in South Africa is wonderfully encouraging, boosting South Africa's role as a global leader in cancer and vaccine research. Can you expand on your vision for our country and the continent at large in this regard?
Well, I think my confidence is not misplaced, right? My confidence is the fact that I was born there, and the confidence reflects I was trained there, and the confidence in the fact that I've been interacting for the last 2 years with some of the top incredible scientists. The talent in South Africa is underestimated, as usual, because we're considered developed. All of Africa considered this developing countries. If one were able to harness this talent, as well as the technology that you can bring almost immediately and transfer into the country. And Shabir, this is where, with the universities, we really need to work with the regulatory authorities, SAPRA, to bring not just SAPRA, but all of Africa, where the standards are equivalent to that of the FDA and the EU, so we can build technologies and, quite ironically, generate next generation technologies and export to the rest of the world from South Africa. So that is the ambition. And it's not a misplaced ambition. I think what you need is really leadership and execution. And I'm grateful for President Ramaphosa to have, as you know, taken on that press conference to expose to the nation that exactly that's what we will be doing. So I'm hopeful that with people like yourself and at the MRC and Glenda Gray, and that we will be able to, and the deans and the amazing scientists, work together and then create a public-private partnership with the government so that we can advance very quickly South Africa as a nation, but really become the technical hub of all of Africa. So that's the ambition, and I'm committed to doing that until somebody knocks me down and says we can't.
Patrick, once again, thank you. I truly appreciate you spending your time. This is the 4th lecture that you've made yourself available to vets during the course of this year. And I think you've had an opportunity addressing the staff, students, and now the alumni. And I think we all really appreciate the time you've spent. and the tremendous energy that you show in your work, as well as your keenness to come back to your home country. So thanks again for all of the time you've allowed us. Prof. Ballard, over to you.
Thank you so much for your really inspiring talk. And yes, we do want to put WITS and South Africa and Africa on the map. And you've shown us that we can. And thank you so much for that commitment and inspiration. I'm going to hand over to Dr. Paul Davis, who is the head of the Health Graduates Association, to just close. Thank you so much again.
Thank you very much, Professor, and thank you, Patrick Soon-Shiong, for such an unbelievably revelational talk. It's not often that we can see the future, and we certainly don't often see it from lectures such as yours. So it's been an absolute wonderful journey that you've taken us through. And it's done wonders for the alumni of WITS, because the alumni are the face of WITS outside of the walls of the faculty. And what you have shown from the WITS alumni diaspora, just what you've been able to achieve. What I really like, I think, about you is that you seem to be a very impatient man, and that you don't, you're not keen to wait for anything. And I really appreciate that, and particularly with your interest in furthering your studies and your insights into the vision of South Africa going forward. There's not much else I can say. There are a million accolades and quotes in the chat column that I'm sure you can relish in your own time. It's been wonderful to be exposed and entertained by you in such an elegant fashion. Thank you very much indeed.
Thank you, Dr. Davis.
Thank you, everyone. Have a fantastic evening. And for those of you in the US, have a fantastic morning going forward. Just to let you know that this talk will be available, I think, on our YouTube channel, on the faculty's YouTube channel, once I've had a conversation with Phil Yang from Networks. Thank you, and have a great rest of the day and evening. Goodbye.
Thank you all. Bye-bye. Stay safe.